Hi, welcome to the project overview of our product, Storage Agents. This project is created for Clemson University Spring 2021 Senior Design Project. The team members are Joe Dorigo, Computer Engineer, Thomas Kennelly, Computer Engineer, Cordell Douglas, Electrical Engineer, Anna Kurosaki, Electrical Engineer, and Deep Patel, Electrical Engineer. Storage Agents is a product that will improve the workflow of warehouses. The objectives are: there are two robots intended to maneuver through the floor plan of a warehouse to pick up items from aisles and drop them off at a designated location. For the prototype, two robots are created to demonstrate the functionality of the product. One car will label blue and then the other red, which have separate instructions to pick up and drop off its corresponding objects and color coordinated drop-off location. Our motivation and inspiration for this product came from Amazon robot called Kiva. Our robots will handle smaller objects. Smaller objects include boxes and packages. Lastly, our robot will be cheaper and easier to manufacture.
The root cause of the design problem came about from wanting to create a smart deployable system that could be used in warehouses to either assist or take over the task of moving materials and goods. Given the previously stated objective, we decided to create the following set of criteria in order to help guide our design process. For the car, we wanted the prototype to move a distance of 1 meter following a given path. This seemed like a reasonable distance because it would show proof of concept of the line following portion of our design. The vehicle should be able to move at a consistent speed of half a meter per second. This would keep consumers interested, as any slower it would be easy to lose interest, as well as make the argument that a worker would be the more efficient solution. And any faster than this speed, we would run the risk of losing control of our vehicle. The vehicle should be able to make 90-degree turns within an accuracy of 10 degrees. This would put less stress on the line following portion of the vehicle, as any movement would be lined up after each turn. The magnet should be able to pick up an object at a location measuring 12 centimeters by 7 centimeters and drop off the object at a similarly sized location. This size was chosen so that even given the worst possible scenario of the car lining up with the drop-off location at an angle, there would be a 2 centimeter buffer on the closest side. The vehicle should have a sensor to alert them if they are within 10 centimeters of each other. We decided to use an ultrasonic sensor for this portion because it gave the most accurate readings. Whenever a vehicle was within this distance, an object avoidance procedure would take place so as the cars would never hit each other. The vehicle and magnet should both be powered by the Arduino's 5-volt power supply. By handling the power this way, we would be able to have the vehicles untethered from the laptop running the image processing and route determination software. For the software portion, we decided to have a camera capture a 640 by 480 pixel image. This seemed like a relatively small size. However, as we started working, we realized it took too long to process with the algorithm we had created to determine the route. We then took the image and compressed it to a 64 by 48 pixel image, which was then converted to a 64 by 48 integer array. We decided we could not compress it any further than this after testing because we discovered issues when trying to identify lines for the vehicle to follow. This array contained a hashed value that was the average color for each pixel in the compressed image, which made image processing and route determination much faster than previous.
Our final design consisted of two cars, red and blue. Both included a 3D printed case to cover up the underlying circuitry and hardware. The final floor layout was made up of a 60-inch by 40-inch poster board, along with red and blue duct tape with a strategically hand-drawn black grid path, along with 4 magnetic wooden objects. And to make the process of running our product quick and easy, we created a GUI with 3 simple features for the user to run. Our final design's hardware consisted of 5 main components, all connected to our Arduino Uno and powered by the 5-volt output. The first component is the HC05 Bluetooth module that is connected to the COM ports of our Windows laptop and receives route inputs from that laptop. The second component is the L293D motor control IC and the 2 DC gear motors. These are controlled with the Arduino based on those given instructions. The third component is the left and right infrared line following sensor. which reflects light from one diode to the other diode and will go high when the vehicle is crossed over that black path. The fourth component is the HC SR04 ultrasonic distance sensor. This sends out a pulse frequency and will receive it back after it hits off of an object. It will take that duration of time for it to hit an object, and it will use that to calculate the distance it is from that object. The fifth component is the electromagnet, which is toggled on and off depending on if there is an object needed to be picked up or dropped off. Our final design for our software consists of two major parts, the laptop software and the vehicle software. For the laptop software, everything is controlled with Python. It is used to capture a live image of the floor layout and process it into a pixel matrix with values of 0, 1, 2, and 3, which correspond to white, black, red, and blue. Based on these pixel values, an algorithm determines the location of the vehicle, the objects that vehicle needs to pick up, and the shelf that it needs to drop those objects off at. It then creates a vector of instructions that are sent via Bluetooth to the cars, telling it how to proceed along the path. For the vehicle software, it receives the instruction vector, and based on the input instruction, it will control the motor and other I/O devices to perform that specific task, all while maintaining its position on the line and avoiding the other vehicle. Once an instruction is completed, it will move on to the next instruction from that vector until all tasks have been completed, and it will stop.
For the strengths and weaknesses, the computer vision, electromagnetic control, and Bluetooth control systems were partially stable and consistent. The code written for the image processing and route determination was completed relatively quickly and gave no issues when processing the image of the floor layout. The electromagnetic control subsystem was easy to build, as a similar subsystem was created in the previous course. Once wired to the Arduino, there were minimal issues with picking up and dropping off the magnet. A couple of times, the electromagnet did not drop off the object when instructed to do so, but that had to do more with the object's weight, as the electromagnet demagnetized as required. Once the Bluetooth connection was set up, the car had no issue receiving the instructions. The only obstacle faced in the Bluetooth control subsystem was when the Bluetooth connection was lost. However, this only happened a few times out of countless test runs done. The motor, control, line following, and object sensor subsystems proved to be far more inconsistent though. Since the motors ran at different speeds when given the same power supply, it was difficult for the car to run straight and make consistent 90-degree turns. There were times when one motor proved to be stronger than the other, but after a couple of runs, this would change. The power of the battery supplied also affected the power supplied to the motors. When a fresh battery was plugged in, the power supplied to the motors was stronger than before, causing the car to overturn. Due to this inconsistency in motor power, the project relied heavily on the line-following subsystems to keep the car on the path that would cause it to deviate. For the first month, one method of line following proved useful and successful when testing on small scale. However, when the final layout, which was 6 times the size of the small scale layout, was used, the line following method proved inconsistent. In the end, the line following process was revised, which kept the car on the path consistently. Finally, the HCSR04 object sensor used in the object sensor subsystem proved to be overly sensitive. There were multiple times when there was nothing in front of the car and the object sensor would read an object. This detection could have been caused by dust. Therefore, the car would operate as if there was another car in front of it when there wasn't.
Our project was measured qualitatively to determine if it was meeting each of the required specifications. During the first milestone, we built and tested the Bluetooth control, motor control, and line following subsystems. To ensure the Bluetooth was working, we would send instructions to each car via laptop and see if they would receive them. For the motor control, we would send instructions to the car to move in a straight line for half a meter and complete a 90-degree turn and 180-degree turn. This was a long trial and error process to meet these requirements due to the inconsistency of the motor power. Finally, the line following subsystem was tested by making sure the car doesn't deviate from the path by 5 centimeters. For the second milestone, we focused on the image processing and route determination, electromagnet control, and object avoidance subsystem. For image processing and route determination, the Python code would process the image of the layout to determine the paths and route for the vehicles. To make sure these were correct, we would look at the array of directions for each car and make sure they complete the necessary tasks. To test electromagnet control, we would run the cars and make sure the car would stop within 6 centimeters of the pickup and drop-off location of the object. The electromagnet would also need to consistently pick up the object, stay magnetized until the drop-off location, and drop off the object. For the object avoidance, the two cars would need to detect each other within 10 centimeters of each other and be able to maneuver around each other to complete their task. This is the final demonstration of our prototype storage agents. On the left is the user interface GUI, and on the right is the live video feed. The user interface captures the image of the floor plan and processes it to determine the instructions for each car. This is then sent to the cars via Bluetooth. As you can see, when the cars are about to collide, the blue car moves out of the way and gives the red car priority. Once the red car passes, the blue car gets back on the path to accomplish its remaining tasks. The jerky motion of the cars is due to the line following subsystem. This is the car auto-correcting itself to remain on the path. Each car moves to its color-coded designated shelf to pick up its object and drop it off at its corresponding drop-off location. Once the cars drop off all their items at its designated drop-off location, it then returns back to its starting position. Thank you for watching and have a great day.